The morphogenesis of the biological beings is a quite complicated issue. According to many multidisciplinary studies, including the accretive growth of some crustacean surfaces, has been made by different scientists. Capturing the outlines of 2D objects is also a substantial topic in computer-aided geometric design, and curve fitting with Bézier curves is a traditional method in this process. The elastic behavior of rods and beams, which attracts continuous attention since the time of Galileo, Bernoulli, and Euler. Elastic curves, as a curves being in nature, has complex parameterizations. In the study, we combine all the theories mentioned above just for describing the kinematics of the growth process of real-life objects. The accretive growth of a surface in the Euclidean space is introduced in 1. It is considered a generating curve R0 in plane at a time 0, and the velocity vector field Q represents the local direction and rate of the growth at each point. This velocity field gives the evolution of the generating curve and defines a surface. And let R be a smooth curve and D1, D2, D3 be an orthonormal frame attached to that curve, and we will use the Fresnel frame, and we will choose D3 as the tangent vector. And here lambda is a stretch factor. We have U and W matrices, which are the Darboux matrices describing the rotation of the local basis at a given time t, and the angular velocity of the local basis at a fixed point s, respectively. Once the generating curve and the attached frame are known, the surface can be written as this differential equation. We assume Q bar is the velocity expressed in the local frame under the assumption of the differentiability on the surface and using the orthonormality of the general basis. We have these two equations, and we can rewrite these equations in the means of components as these: a set of 6 nonlinear first-order partial differential equations for 7 dependent variables. Then the accretive surface is obtained by integrating this equation. Since we use the Fresnel frame, the Darboux matrix is in this form. Lambda is the stretch factor. The accretive surface is determined by choosing a frame, providing a structure for the growth velocity. Here we note that the velocity must have a component in the binormal direction to construct the surface. Then solving the system. In this section, we give a brief information about the planar elastic curves. A planar elastic curve is described by gamma together with specified endpoints and tangents and length, which minimizes the bending energy given by this integral. Also, the curvature of an elastica at all points proportional to the distance to a fixed line, which is called directrix. If theta is the tangent angle function of a unit speed elastic curve, then derivative of theta equals kappa, the curvature, and the curve satisfies the following Euler-Lagrange equation. For some Lagrange multipliers, lambda 1 and lambda 2, we set lambda 1 and lambda 2 as this: lambda cosinus phi, lambda sinus phi, and this gives a simpler version of the Euler-Lagrange equation. If lambda equals 0, the differential equation becomes this. So the curve is part of either a circle or a straight line. If gamma is an elastica, then the scaled and rotated curve gamma bar, defined by this, is also an elastica. This is important because we make rotations and scalings while constructing the accretive surfaces. Explicit parameterizations of the elastic curves are given as follows in A, B, and C. Here, E and F denote the incomplete elliptic integrals of the second and first kinds, depending on the argument UN modulus K. And AM denotes the Jacobi amplitude function. Here we have the illustrations of the elastic curves in A, B, and C from top to the bottom. In all cases, the parameter lambda is 4. We take the elastica B as the initial curve for an example. Then we choose a growth velocity Q. This growth velocity gives a constant growth in the rectifying plane of the initial curve at every point. Then we solve the system of PDE and take the integral. So we have this accretive surface. However, when we use an elastic curve as the initial curve to evolve and create a surface, the system of PDE given in the equation 1 is quite difficult to solve. Hence, we make an approximation to the elastic curves by using the cubic Bézier curves for obtaining polynomial expressions. This method would be very helpful in the calculations when someone needs to use the curves defined in more complex forms in the nature. The general equation of a cubic Bézier curve is determined by the Bernstein polynomials as this. Here, Kr are the 4 control points. An example is this. K0, K1, K2, and K3. The parameterization of the Bézier curve, and this is the illustration. If we change the 2 control points in the middle as K1 and K2, these 2 control points, while the start and end points remain the same, we have this curve. Now we assume that K0 and K3 are 2 consecutive points that we aim to fit, while K1 and K2 are the remaining 2 control points that we need to predict. Take gamma I as the Bézier curve that fits pi to pi plus 1, and it has this form. Now we need to determine the coefficients A1 and AB here, A1 and AB. Moreover, for the final curve to be smooth, the transition between gamma I and gamma I plus 1 must be smooth around the point pi plus 1. That means the curvatures of 2 pieces matches. Then we have following conditions. Since we have n curves, we need to find 2 n variables to determine AI and BI. However, we only have 2 n minus 1 equations. Therefore, we give the following boundary conditions. And we calculate the first and second derivatives of gamma I and substitute in the last 2 equations. We have 2 n equations as follows. When we eliminate all the BI by using the first and second derivatives of gamma I, then the equations become this. Matrix representation of the above system of equations is like this. And we can find the coefficients BI from the In the light of the above method, we find the best approximation of the elastic curves with the help of the cubic Bézier curves. We give the computer algorithm related to Bézier curve fitting and the elastica and constructing accretive group surfaces as, this is the algorithm. Here we give an example. Let me choose the elastic curve given in C. I can show it. This curve is C. If we take 8 pieces, it means 16 pair of K1, K2 points. We calculate the coefficients AI and BI as follows. However, we need more pieces to obtain best results. The following figure shows the resultant curve for 8, 16, and 32 pieces, respectively. From top to the bottom, 8 pieces, 16 pieces, and 32 pieces. We define a constant growth in the direction of the binomial vector at every point. So Q is 0, 1, 0. We calculate the frame apparatus at every point on each pieces of the Bézier curves and calculate the accretive surface as a cylinder like this. Another example is this. Let we choose the elastic curve given in A. The following figure shows the resulting curve for the approximated curve for 16 and 32 pieces respectively. Blue one is the approximated curve. Choosing a constant growth in the direction of the binomial vector at every point on each pieces, then we have the accretive surface as a cylinder again.
You have 2 minutes left.
Okay. The unwanted rotations of the frame at the inflection points. Here at the inflection points, binomial vector changes its direction. So it can be removed by choosing the attached frame as a rotation minimizing frame. It can be determined the error between the methods of the original form and the Bézier curve fitting. The growth velocity can be developed to more complex forms such that it includes rotations and scalings. We chose growth velocity as constant in our examples, but it can be developed. Hence, the growth of more complex structures may be explained. These are the references. Thank you for attention.